Thank you. So the work I will present today is, well, a combination of several works that we did with Elena Castellani, Henk de Recht, Dennis Dix, and Jeroen van Dongen in various constellations. So it's going to be kind of, I mean, until now I had kind of a systematic line of thought. Today it's going to be more presenting various aspects of this heuristic way to use dualities. So I have 3 points. First, to define what I mean by a heuristic function of dualities. Then the question about duality and emergence, which appears quite a bit in physics. When people talk about duality, then very often they go into the topic of emergence. And then in the second half of the talk about scientific understanding and dualities. And of course, scientific understanding is a big topic on which there has been quite some work since the 90s by De Recht and Strehl and some other people. So I will summarize some of that and then mention our own contribution to that. But I begin with a heuristic function of dualities. So it's about effective dualities, which we have already discussed, and the notion of successor theory. So what kinds of use of dualities do we have? So far, we have mostly talked about dualities that are exactly instantiated. We have 2 models that are dual, and then we find a theory that is of which those models are representations, and we have called that a common core theory. So this role of duality, discussing, for example, things like equivalence, that was closely tied to satisfying the schema, to having this exact duality. But on the other hand, dualities are standard tools for theory construction in physics, and they have been quite instrumental in various discoveries, like, for example, position-momentum duality in quantum mechanics, Gauss-Vannier duality, so that it was instrumental in, well, making the prediction about the phase transition in ferromagnets, making a prediction for the critical temperature in that model, but also for Onsager's solution of the 2-dimensional Ising model. And we have also seen applications in string theory and in quantum field theory, for example, the 't Hooft-Wannenstam idea that you could have the confinement of quarks, that could be the dual effect of the Meissner effect. So if you have a superconductor, the Meissner effect, thereby the magnetic field is expelled, so there is no magnetic field penetration into the material. And their idea was that you could have something similar for electric fields in QCD, so for the charges of quarks, and that would entail, rather than the condensation of electrons in Cooper pairs, that would entail condensation of magnetic monopoles. So they used again the idea of duality there. We've seen it with Polchinski, discovery of D-branes and M theory. The Seibert-Witten work on S-duality in 4-dimensional n equals 2 super Yang mills. The Strominger calculation of black hole entropy from D-brane counting. So their dualities also played a key role in the actual calculation that they did of calculating the entropy of a black hole out of a configuration of D-branes and using various dualities. And then all of that led up to Maldaceno's ADS-CFT correspondence. So we see that the idea of duality can be very fruitful in this sense of new theory construction. And here I would like to make this distinction between 2 functions. On the one hand, we have what I call the theoretical function, where the aim is to develop a theory that is common to these 2 models, so that the models are exactly instantiated. That's what we've discussed so far. The other one is the heuristic function, where we look for a successor theory. So we look for a theory that goes beyond the models that we already have. And so that theory will not be, the duality will not be instantiated in that theory, or the models will not be exact representations of that theory, precisely because it goes beyond the two models. And I will give some examples in a minute. So I would say that the philosophical discussion of dualities has mostly focused on the form, on the theoretical function, because of course philosophers have been interested in things like empirical equivalence, theoretical equivalence, and things like that, for which we need for which we use the theoretical function. But when physicists say that duality points to new physics, then they often, I claim, and I hope to substantiate that in the examples, is that they have this heuristic function in mind many times. So let's see in slightly more detail what we mean by what is the theoretical function. I've already said it, but the aim here is to develop a theory that is already given according to certain constraints. By already given, I mean that, okay, we have models, and we know, or we conjecture, that they are instantiations of a duality, representations of a theory. And the only thing we need to do is we need to prove this. We need to find this theory, or we need to prove the duality conjecture. So it's like when you have a conjecture of a mathematical theorem, and then you need to fill in the details. But the result, the end result, is in some sense already given. So examples of this are, given a Hamiltonian, find the equations of motion. So in that process, there is no real physics. You don't need to introduce any new degrees of freedom or any new fields. You already have the Hamiltonian, and you go through a mathematical derivation that gives you the equations of motion. Or given a state and a symmetry transformation, find a symmetry-related state. Now, these are problems that can be hard mathematically, but they are mathematical problems. They are not per se physical problems. Also find a formalism that encompasses both x and p, for example. So find a Fourier transformation. So for dualities, that would be the idea of prove a duality conjecture between already given models. And in fact, we have some. I mean, we have many of those. For example, T-duality, which we have discussed. So people think that it is an exact duality, at least order by order in perturbation theory, in type 2A, type 2B string theory. But there is no exact proof. So that's the idea of the theoretical function. Now that contrasts with the heuristic function, where typically there are no mechanical rules or no even mathematical rules, but where we do need to add things, new things, physical new things, like new degrees of freedom, new fields, new dynamics. So the result here is really a new theory, often also with a new interpretation. And in fact, I will also claim that the idea of interpretation is also quite important here to find a new theory. So the novelty is in the number and the nature of degrees of freedom, in the dynamics, and in the interpretation. So there's quite some novelty involved. An example would be find the Hamiltonian for a given physical system. So if you give me a physical system, find the associated Hamiltonian. That can be a hard problem for which there is no predetermined procedure. There are rules of thumb, and someone with a lot of practice could kind of do it quickly, but it's a matter of basically trial and error and practice. So it is not a deductive procedure. We begin with some phenomena, and then we try to fit our formalism of the Hamiltonian formalism to that, and try to find what's the relevant Hamiltonian. So for dualities, the idea would be apply duality to cases where duality may only hold approximately. So there is an effective duality, but there is no exact duality. That's the basic idea. So let me say a bit more about this notion of effective duality, which has come up earlier already. So an effective duality is an approximate instantiation of a duality, of the idea of a duality. We saw the example of personalization in 2 dimensions is an exact duality, is a duality, but if we go to 3 and 4 dimensions, then so far as we know, there is not an exact personalization, but there are things that are close enough. So there are limits of personalization. So you can find, for example, a boson as the infrared limit of a complicated fermionic system, where you integrate out the high energy degrees of freedom, and you end up with an effective theory that is described by a boson. So in that sense, there is some kind of personalization, but it is only in a particular limit. It's not exact. So that's an effective duality. So there's no isomorphism of model roots, although there's something similar. And so there is, in general, no common core theory. Although physicists often do expect to find a successor theory that goes beyond, but even that is, of course, not guaranteed that there will be a consistent successor theory. But if this idea of effective dualities to be, or the idea rather of heuristic functions to be unuseful, then the aim is to find the successor theory. So the heuristic role of the idea of duality then is that it helps, it motivates physicists to construct this successor theory, and that if they do find a successor theory, then this will explain the existence of the effective duality. So there is something that you gain by finding this successor theory. Namely, you get an explanation for why these 2 models were so close to each other. So here's what I mean by heuristic function then. We find a successor theory that I call T sub S that encompasses T1 and T2. In what sense does it encompass them? Well, it explains the physical origin of the duality or of the effective duality. Duality, if there is one, is a property then of idealized or special theories, of particular limits of the theories, but not of TS as such. So TS reproduces T1 and T2 special cases or particular approximations, limits, and if there is an effective duality, that will be, if there is an effective duality, then T1 and T2 need not be exact duals. So perhaps duality breaks down and T, so the common core theory does not even exist. So TS usually involves also a new interpretation of T1 and T2. Okay, so in the heuristic function, it's essential that if there exists a common core theory, T, then it will be different from the successor theory TS, because otherwise, if they are the same, then this is just what I call the theoretical function. If there is a heuristic function, then you are going beyond the idea of exact duality. Okay, so and for this reason, for the talk today, there will not be a need to emphasize the word models like I did before, because now they are not exact instantiations of this theory. They will only be approximations, and so I can therefore simply talk about theories. Okay, now how does this appear in the physics literature? If you read the physics paper, what do they say? So both functions are expressed in the physics literature, and this distinction between heuristic and theoretical actually reflects a scientific disagreement about the unifying theory underlying a duality conjecture. For example, I already mentioned in T-duality, the conjecture is that there is an exact duality between type 2A and type 2B, at least at the perturbative level, so order by order in alpha prime. On the other hand, people seem to agree that there is not an exact duality between the strong coupling limit of type 2A string theory and M theory. That is supposed to be only an effective duality between type 2A and 11-dimensional supergravity. So you see the difference in those two examples. One is conjectured to be duality, the other is conjectured to be only an effective duality. And so that really reflects, well, I said, maybe it's somewhat strongly put here, scientific disagreement, but yeah, I mean, different scientific views that you can have on the question, is this a duality, yes or no? And the reason I mentioned scientific disagreements is that in the papers, actually, people give various different verdicts about the different examples. Nevertheless, these two functions, I claim, do not lead to contradictions because they simply exemplify different ways in which theory construction can be approached. So precisely because TS is not equal to T, they are different theories, and so there's no contradiction in these two ideas. They are simply realized. The two ideas are realized by different theories. Now, unfortunately, in the literature, the literatures sometimes or often quite ambiguous whether they mean the theoretical or the heuristic function of duality, and this might also have led maybe to the lacking attention for this heuristic function also in the less attention has been paid to it in the philosophical literature. I should say people like, for example, Dean Rickles, he has mentioned it in some ways in some of his papers. So the official definition of duality is isomorphism of theories, but physicists are often tempted to use the word duality when they actually mean effective duality. I gave in my paper, that is called something like the heuristic function, I gave a number of quotes from various papers by Witten, by Robert Dijkgraaf, by Maldacena, various string theorists especially, where you could see that they were, some of them were talking about duality, others were talking about effective dualities without really making the distinction. Now, I was happy to hear at Strings 21 last year, there was a comment about, a brief comment about this by Hiroshi Oguri, commenting on Haroni's talk, who had, so Haroni had called to make this distinction also in the language between duality and effective duality. So physicists are also have this distinction clear in their minds, even if they don't always articulate it. But I think that especially for us philosophers, it's very important to make this distinction. So dualities in string theory. Okay, so this is has been general about what is the heuristic function of. It's quite straightforward. Now I want to say something about the actual examples and how this plays out. So here I have, well, two slides that I are kind of introducing this M theory program. We already discussed the examples 2 days ago, but we didn't actually discuss M theory and the unification idea, so I will do now. So we discussed that initially there were 5 string theories, T-duality between type 2 string theory on a circle of radius r and on a circle of radius 1 over r, and then S-duality of type 2b string theory, where we invert the string coupling. And then Witten in 1995 discovered that the 5 string theories plus 11-dimensional supergravity, that they were all different limits of a given, a single underlying theory. And the idea was that the 11-dimensional circle is the radius, is the coupling constant of the string theory. And we had the formula a couple of days ago. So for a small circle, we have a weak string coupling, and the string theory description should be accurate, while for a large circle, the string coupling is strong and the perturbative string theory description is not valid. He also conjectured that 11-dimensional supergravity comes in when the circle becomes large, because then we go to 11 dimensions. So we get this M theory conjecture. And the challenge is to find a theory that is valid away from the point particle limit. So the point particle limit of M theory is supergravity, and also the classical limit of that theory. But what happens when you go beyond that limit? That is, of course, the question. Now, to see, so this is the connection with type 2. To see a connection with type 2b, it is best to reduce to 9 dimensions. So you see here on the slide that we go from 11 dimensions. So we have supergravity on, well, initially, I mean, we have supergravity on 11 dimensions, and we can compactify it on 2 subsequent circles. So we have R9 times S1 times S1. So 2 circles of 2 different radii that are called R10 and R11. We take R11 to be small, so that we are left effectively with a 10-dimensional theory type 2A on R9 times S1. That's the usual correspondence. We can do a T-duality on that. If this R10 is small, then we end up with type 2B on R9 times S1 on the dual radius. So the radius R tilde is now if R10 is small, then R tilde is large. And so effectively, that will give us type 2B on R10. Now, type 2B on R10 is known to have S-duality, as we already said. So the question here is, what is the M theory origin of S-duality? That's the question that was unclear, because this type 2B, even though it can be related to type 2A, and we know how it comes from M theory, it's not clear how S-duality, where it comes from, because type 2A does not have S-duality. Now, to get insight into that, we go further to 9 dimensions. So we compactify on this further circle. So we are left with type 2A on R9. We take R10 to be small. And so now we see that type 2A and R9 via the same chain is going to be related to type 2B on R10, because type 2 and R9 is simply the small R10 limit of this type 2A here in the middle line, and that is simply dual to type 2B on R10. So now we should be able to understand the type 2B, the S-duality of type 2B on R10 from the type 2A on R9. Now, what property of type 2A on R9 hints to S-duality? Well, so let's see what we have. So we have now an effective, if we link the two, basically the two coordinates that we have linked here at the bottom of the slide, 11-dimensional supergravity on R9 times a 2 torus, where this 2 torus is S1 times S1. We have connected that via these dualities, or via this duality, with type 2B on R9 times R10 on this dual S1. So here is again the expression of S-duality that I've mentioned before. The S-duality group as the SL2Z group, similar to what we saw for n equals for square and mills. So now using this chain of duality, we get that the string coupling constant in type 2b is given by the ratio of the radii R11 divided by R10 by the chain of duality. So now we can see how S duality acts on the radii, because S duality, third bullet point says GS goes to 1 over GS. So that means that R11 over 1, R10 is going to R10 over R11. So basically we interchange these two radii. So we have here the torus on the figure. It's a torus with two radii. R10 is the small cycle, the B cycle, and R11 is the large cycle, the A cycle. But the S duality exchanges these cycles. The area stays the same, but there is a different complex structure. So the conjecture then is that if this chain of dualities is true, is that the SL2Z S duality, I mean, this suggests, the calculation via the correspondence between the coupling and the radii suggests that S duality of type 2b can be reinterpreted as the diffeomorphism symmetry of the torus in 11 dimensions. And there were further checks of this done by Schwartz and Russo and Zeidman, where they calculated various quantities, not just in the massless sector, but also for the massless sector, and they found agreement. Okay, so that's how now we got also our type 2b string theory into the picture, even though it's not directly connected to 11 dimensions, but it is connected to 11 dimensions via this 9-dimensional route. Okay, so this then prompted what we mentioned before, a series of duality conjectures. People were asking themselves, what is the theory behind all these conjectures that we have found? And we've already discussed several approaches to M theory. We still don't know what M theory is. We know some of its properties. We know that at low energies, it should reproduce 11-dimensional supergravity. We know some of its quantum properties, which can be obtained from quantum properties of type 2A string theory. And so there were various conjectures. One is matrix theory, which we already discussed. So basically the idea that we have a discretization of membranes in 11 dimensions by means of D0 branes whose coordinates are non-commuting coordinates in 11 dimensions. So D0 branes, they are point particles in 11 dimensions. They interact with each other. If they are close together, they form a membrane. Macroscopically, it looks like a membrane, but microscopically, it's really a non-abelian configuration of these particles that interact with each other, and their coordinates are non-abelian because they are matrices. So that's the basic heuristic of matrix theory. The other approach is ADS-CFT. I say that this is an approach to M theory in the sense that one of the ADS-CFT cases involves ADS in 11 dimensions. So it involves either ADS cross S7 or ADS7 cross S4, so either 11-dimensional versions of the conjecture. And so by studying this CFT, we should be able to find something about those 11 dimensions. So the question is, should M theory exhibit duality, or are dualities superseded in the final theory, in M theory? Are they merely ways towards the formulation of a new theory, and can we forget about the dualities after we have found this theory? And the answer to this question is not at all straightforward. So like I said, there are different attitudes, different answers, implicit answers to these questions in the literature. In my paper, I gave explicit quotes about that. I will not go into them now. It would be too long, but So my analysis is that if you can speak of a consensus, the consensus would be that with respect to the specific question of the M-theory dualities, so not the string theory dualities, but M-theory itself, it seems to be that it is really about the heuristic function. So that M-theory is something that is kind of above its theory by itself, and that the other corners here are merely limits of that theory. I should say not everyone agrees here. For example, John Schwartz is one of the people who has a different view. He says that M theory doesn't stand above, but it's just itself one of the approximate corners. So he has a view of these dualities more of like a manifold, where you have a manifold with different patches and there. So there are various views, but I mean, in some sense, that is also part of the heuristic function, but the idea of what should be the TS, that he has a different conjecture for that theory. Okay, so this is how this heuristic function functions concretely in string theory. And like I said, it's not always clear in the discussion by physicists. In fact, it is very often obscure, and I think that can lead to mistakes. It can lead to wrong conjectures if one is not careful. Even though, of course, working physicists will usually have in the back of their minds a clear statement of duality, but it is for the conceptual analysis, it's important to separate those things. Okay, now I would like to go on to another.
Sebastian, may I pose a question? In this last slide, you spoke about the final theory. What do you mean with final theory? Because it is clear that now we know that there are at least 4 important forces: gravitation, weak electromagnetic, and strong forces. And we know that we have a problem in putting together gravitation with standard models. That is a good way to explain the other 3. But we know also that in the universe there are 95% of what there is that is substantially unknown. So perhaps I understand that if a string is able to, will be really able to put together gravity and the standard model, in a certain sense, is a step forward. But perhaps from an epistemological point of view, to adopt this theory, final theory of the M theory, without considering the fact that 95%, we know that 95% of what there is unknown, perhaps it's not a good name, or I am mistaken.
Yeah, thank you for the question. Notice that I don't think I mentioned, I mean, I'm sure I didn't mention the word, the final theory. Okay, yeah, it is here, very good. Yes.
This final theory that make me think about this point, yes.
No, by final theory here, I mean within the string theory program. So it's not final theory in the sense of a theory of everything. So this is separate. So this is really within the string theory program. So there's of course the question of what is, so how does this connect to observations, and then you come into the whole discussion about the string theory landscape. So string theory itself has a landscape of possible solutions where our universe could be one universe within that possible set of solutions. But what the program is here is to, at least for the purposes of this talk, is to see where the idea of duality leads us. So from the requirements of consistency, of formulating theories of quantum gravity, where does it lead? Where does it lead us? We could do the same thing with other types of dualities, like for example, dualities in quantum field theory. We could play the same game if we have evidence for which well, I guess there might be some for similar kinds of connections in quantum field theory. So by saying that, well, we have this unifying theory, it doesn't necessarily mean that we have the final theory of the universe. It just means the theory that unifies these 5 string theories, or the 5 string theories, and the 11-dimensional supergravity. Okay. So the second aspect then about these dualities that you often see in the physics discussion is the and which is also I would say not always very clear, is the issue of duality of emergence. So suppose that we interpret dual models according to their common core. So we have 2 dual models in the usual way, and we have a common core. And this is a widespread interpretation in string theory for exact dualities. Now, could it be that when we have such an exact duality, that one model emerges from the other? So for example, that N2 emerges from N1. And this is something that, again, in the physics literature is often claimed. For example, here's a quote from Horowitz and Polchinski in 2006. They write, ADS-CFT duality is an example of emergent gravity, emergent space-time, and emergent general coordinate invariance. But it is also an example of emergent strings. We should note that the terms gauge gravity duality and gauge string duality are often used to reflect these emergent properties. Now, there's a lot of things emerging here. So space-time emerges, general covariance emerges, strings emerge, and in fact, in the last sentence, they say that in some sense, gauge gravity duality are often used to reflect these emergent properties. So they seem to be saying that somehow duality is another word for emergent. This might remind you of the discussion of reduction and emergence in physics, where emergence for physicists is very often the same thing as reduction. Of course, for us philosophers, that's quite surprising. But there is this interchangeability of duality and emergence seems to be playing a role here. If not interchangeability, close alliance, as you see here in this sentence. So what is going on here? And I think, I mean, in my view, of course, there is a charitable way to interpret this sentence so that it will make sense, but on the other hand, it's so vague that you can always interpret in. But in any case, there is, at the end of the day, I want to argue that, yes, it is correct what they say. I mean, that there is a way that we can make sense of this, but how should we make sense of it? So what I would like to argue is the following. Since we have M1 and M2 that are isomorphic, and furthermore, their interpretations are the same, because I'm assuming the case that we discussed yesterday of internal interpretations, which is also what they assume in their paper, then there is no relevant sense in which one emerges from the other for the following reason. And it has to do with the formal requirements that you might want to impose to your notion of ontological emergence in physics, in physical theory. So specifically when we talk about, like we are doing here, of emergence of one theory in physics from another theory in physics. So unlike, I mean, there are other cases of emergence. You can have emergence of properties or models, but for the case we are discussing here, duality is a bijection, as we have seen, so that requires that we have we have an equal number of elements between the two models. That's a requirement for a bijection. And emergence requires, and the formal requirement of emergence is that it is a surjective and non-injective map. I call it a linkage map between the two moles or two theories, as I am using them now. And that requires, because it is non-injective, it requires that they have different number of elements. One way to think of it is when you think about, for example, the idea of coarse graining. When we do coarse graining to get emergence, we integrate out degrees of freedom, or we sum them out, or we cluster them together. And so effectively, we reduce the number of degrees of freedom so that the two theories cannot have the same number of degrees of freedom. They cannot have the same, their state spaces cannot have the same dimensions.
Could I see your definition of emergence on it was on the previous slide?
No, it's so on the previous slide was the quote. So the definition of emergence is actually on this slide. So here is the formal requirement. So here's the formal requirement of emergence. It's this this second little bullet point here.
Because that's a definition.
No, that's a requirement. That's a formal requirement of emergence. So I'm adopting the same strategy as yesterday. I have a formal requirement and then I have an interpretive requirement. So already what I'm saying is that already the formal requirement is at odds with the idea of duality, because the formal requirement is that they must have different number of elements for example, if we want to do coarse graining, while duality requires that they have the same number of elements. So already for that reason, this cannot work.
So like a non-trivial kernel.
Yeah, exactly. However, I will say that there can be emergence of at least 3 other types that I'm going to list here. So one of them is when we have effective duality. Obviously, in that case, we can have emergence of any type, because then the duality is somehow broken, and so we don't have this isomorphism requirement, and so the formal requirement is simply not there. So there is no problem in this case. And in fact, this is one of the cases that physicists are often thinking of. The second type of emergence is when we have emergence alongside duality, and this I will show the next slide. But basically, the idea is that on both sides of the duality, we have emergence from both sides of the duality rather than across the duality relation. So what I was discussing here in the top of the slide is when the emergence is really among the same set of theories. It is only in that case that there is a formal inconsistency. But if the emergence is, if we have two duals and the emergence goes in a different direction from the duality, then also there is no problem. And then the third type of emergence is what I call epistemic emergence. And of course, in the literature, there are various definitions of this contrast between epistemic and emergence. In my own account, the contrast, the main thing about the contrast is that epistemic emergence, it's summarized by the contrast between these two diagrams here. Epistemic emergence is novelty. I follow Butterfield's definition of emergence, of novel behavior relative to an appropriate comparison class. Now here, the comparison class is the bottom theory. So here you see at the bottom of the slide, you have the bottom theory, T sub B, and the top theory, TB. Those are, TB is what is the formal part of the theory that emerges from TB. So in epistemic emergence, the emergence is not in the world or in the interpretation. It's not something about the semantics of the theory, but it is something about the mathematical descriptions or about the approximations that we make. So it is something about our theory, not about the world. So that's why we have this commuting diagram here on the left. That's a case of epistemic emergence. You see TB and TT. You have a domain of application, and well, same idea we're talking about yesterday. the interpretation maps, they both map to the same domain of application in the world. So we describe the world using a different formalism, but what we describe is the same. And so the formal requirement of that is that the interpretation map commutes with the linkage. This linkage map is the relation between the two theories. On the other hand, in ontological emergence, that's the case when since the two domains are different, we can formalize that by saying that the interpretation map does not commute with the linkage map. Okay. So that's and so we can certainly have epistemic emergence. So now I would like to illustrate the second, and by the way, you can, like I said here at the bottom, you can combine these three types of emergence can be combined, especially the epistemic emergence with previous ones. So let me now illustrate this idea of coarse graining. We did this paper with Beek, Solomon, and myself a few years ago. In this figure, we were analyzing a specific model of holography by Erik Verlinde. It's somewhat related to ADS-CFT, but it's not quite ADS-CFT. So here what you have is, we have a duality, holography, between a microscopic theory on the boundary of the sphere and the sphere and the theory in the bulk of the sphere. And there's a question mark here on the on the bottom right, because there is a conjecture whether the microscopic theory really exists. We don't know that. So in his model, Verlinde does a coarse graining procedure on both sides of the duality. So where he goes from the microscopic theory to the macroscopic theory by coarse graining. And so he gets a macroscopic theory, which in one description is a macroscopic theory on the boundary. It's a theory that basically loses information somehow. So we have aggregation of states into macroscopic states, while on the other side of the duality, we have a theory of gravity. We reproduce Newton's gravity on a particular set of screens that are related to sets of constant potential, Newton potential. Now, the idea of emergence here is that emergence happens along the vertical direction, and it could happen on both sides, while the holography goes in the duality side. So obviously, in this kind of scenario, there is no problem. There is no incompatibility between holography and coarse graining, simply because they are different procedures. They are along different axes. Same happens for ADS-CFT types of situations, and there are different ways to represent that, but one way is to begin with, let's say, the fundamental string theory or quantum gravity, if such a theory exists. So that is on one side, on the right. On the other, on the left-hand side, we have a CFT, a weakly, possibly weakly coupled CFT. And then we let the RT flow go, so there's a deformation of the CFT. And then we go to strongly coupled CFT. On the left side, and on the right side, we get Einstein's theory of gravity. And again, you could say that there is emergence along the vertical direction, but not along horizontal direction. And interestingly, this type of emergence, if there is a duality at each level, so at each step of the flow of coarse graining, then the duality will relate these two theories of every step. Yeah.
Just a notation. So a two-headed arrow means invertible, and a one-headed arrow means non-invertible.
Yeah, exactly. Yeah. So the idea that the string Well, there's this idea in the literature, in papers by Balasubramanian and Krauss and so on, that we can represent the RT flow as the radial movement of, for example, a scalar field. If you look at the radial evolution of a scalar field, so taking the radial direction is kind of our time direction in ADS. And so we reformulate the equation of motion of the scalar field as rather than as a moving in time, moving in space. And in particular, in the bulk, if you are in the peak bulk, then there are high interactions, the geometry is highly curved. So there you really need the full string theory. For example, if you have something like a black hole in the bulk, then you will need to use the full string theory. While the supergravity description becomes good when you approach the boundary. So that is why usual kind of supergravity calculations for ADS-CST, they work well near the boundary because the curvature is weak near the boundary, but then as you go to the bulk, you need to include more and more correction. Okay, so that's that second idea of emergence alongside duality. Now let's look at the third idea, so the epistemic emergence. To give an example, we could sometimes we make a change of variables in some theories so that the theories look different and maybe even the calculations are easier. But such a change of variables need not necessarily be a case of emergence. It could be simply a matter of our convenience that it's easier for us to do calculations, but the change of variables doesn't really have any import on emergence. So at best, there is an epistemic notion of emergence where it is really the way we describe the theory, the variables that we use to describe the theory, but not what is going on in the world. So a case like that could be this exact case of Sine-Gordon massive steering model where we had an exact duality, especially when we interpret it as an internal interpretation. Then we discussed that we really just have two different descriptions of the same theory in a different language. And so we had a calculation that is difficult to do in the fermionic picture is easy to do in the bosonic picture, and vice versa. But it is not really the case that, I mean, both pictures have both fermions and bosons. It's not the case that all of a sudden the fermions emerge or the bosons emerge. They were there in the Hilbert space already from the beginning. So in this case, there is no ontological novelty, and yet there is some appearance through the change of variables as if we had solitons. There are no real solitons in this case, but there is an appearance of that. It's only when you do an approximation that it really appears as if you have reached a soliton solution. Or in other words, I would say that in this case, the usual notion of soliton doesn't really has a different meaning. Okay, or at least you have to be careful about the notion. So this seems to be the kind of emergence that is also often involved for dualities, so not for effective dualities, but for dualities. Simply a matter of convenience, a matter of a change of variables. So those are some of the options we have for emergence. Let's see how we are doing with Tanya. I don't know if there are any comments or questions before I move on. Yes.
Could you go back to
the third one? This one.
But on internal interpretation, there's no ontological novelty. Would you consider inertial motion as a candidate for ontological novelty?
Inertial motion with respect to what? I mean, novelty with respect to what? I mean, I always need to compare two situations.
Okay, well, it's a trick question. So let me see. For example, might look different and calculations are easier. So there's this thing you have in mechanics, symplectic rectification, straightening, whatever. So that's just a change of variables. But something one could call inertial motion results from the change of variables. And I guess some people would call that an ontological novelty.
To be honest, I think I would have to look at the details of the technicalities of the problem, because I'm not exactly sure, what is emergent from what and what you mean.
Well, you get a very general kind of motion with forces, and then you make a change of variables, canonical transformation, and out comes the simplest possible kind of motion.
So to maybe a related example is if I have like a Newtonian theory of, say, n particles that move around and interact, and now I do a coarse graining description where I go to the kind of center of mass. I just look, and maybe that's what you mean. I just look at the center of mass motion of that. So I do a change of variables where I define my center of mass as this, in terms of all the other positions, and now I forget about all the individual particles, and now I just look at the dynamics of that, which is indeed inertial motion. I would not consider that to be emergence, because that would be, I would argue, a case of mere coarse graining, in the sense that we have this initial theory which contains a lot of information, and we simply selectively drop information, but the actual information about the center of mass motion, that was already included. I mean, you can answer the same questions from the original model. So it's simply that we have an initial domain. We have a domain that we begin with, and now we go to a subdomain. So we have a smaller domain, but it's still a subdomain. So in that sense, we have restricted the domain, but it is still part of that domain. Yeah, so actually, in my paper, when I defined the epistemic emergence, I included that possibility that the domains might still be different, but one might be a subdomain of the other. Okay, so now I go to the question. So, question of scientific understanding and how that sits with duality. And this is, in fact, an entirely, in some respect, entirely different and orthogonal topic, but I think it's interesting in its own right. And it has to do with the notion of understanding, the broad notion of understanding philosophy of science. And of course, the debate about how you represent space and time in physical systems, or rather how you represent physical systems in space and time, whether that's necessary, it's a very old debate. And among the logical empiricists, there was the view that understanding is something of the individual. So it wasn't really of interest to philosophy of science per se. At least that was the initial notion. So, for example, Handel writes in 1965 that such expressions as realm of understanding are comprehensible, do not belong to the vocabulary of logic, for they refer to the psychological and pragmatic aspects of explanation. So there was this idea that understanding has to do with psychology and with something pragmatic, not so much with substantial philosophical analysis. Of course, this is very broad brush, because there were differences among the logical empiricists themselves, and they also changed. There was also a change in their views as we go along, of course. But so the idea was that explanation is an objective relation between a theory and phenomena, while understanding, by contrast, always involves an epistemic subject. Yes. And so for that reason, it is it always has it is epistemically irrelevant because we have that sense. This has been emphasized by Derecht and Dieks in a well-known paper from 2005, very influential paper in the literature on scientific understanding and explanation. The question that they ask is it true that understanding is irrelevant to philosophy of science? So, of course, there were already attempts to make that relevance clear before, but I would say that this was the paper that really put that on quite centrally on the philosophical agenda. We think their model visualization plays an important role, and in understanding in general has always played an important role. And in fact, in the history of understanding in physics, also always goes back to the discussion about Anschaulichkeit between Schrödinger and Heisenberg, which is probably known to most of you. So this is where the idea of understanding by Derecht and Dieks got part of its inception from. So Schrödinger wrote, here are some nice quotes, I naturally knew about his theory, so referring to Heisenberg's theory of matrix mechanics. I naturally knew about his theory, but was discouraged, if not repelled, by what appeared to me as very difficult methods of transcendental algebra and by the lack of Anschaulichkeit. So we cannot really alter our manner of thinking in space and time, and what we cannot comprehend within it, we cannot understand at all. So that was Schrödinger's idea. We really need visualization to understand. So understanding without visualization is impossible. That was Schrödinger's basic idea. And of course, it was a way to promote his own theory. It was not just a philosophical theory about understanding, it was also a theory about why Schrödinger mechanics or wave mechanics is a better theory than matrix mechanics.
It's space, that's configuration space, it's not. I mean, it's a dodgy quotation. We cannot really alter our manner of thinking in space and time, and what we cannot comprehend with it, we cannot. Well, he gives the impression that space is just three-dimensional, but it's not. I mean, his waves propagate in n-dimensional configuration.
Yeah. But he would have viewed this as a three-dimensional space. It's a three-dimensional space. Yeah. I mean, he wasn't. I agree. I mean, later developments have changed it, but in any case, I mean, even if you look at a single particle, he would have already for a single particle, he would have said that is we need the visualization. But yeah, you are saying, you are making a fair point that doesn't really work because your visualization should be in a 3n dimensional particle. I think that's right. 3n dimensional space. That's a okay. So how does Heisenberg reply to Schrödinger? He says, the more I think of the physical part of Schrödinger's theory, the more appalling I find it. What Schrödinger writes about Anschaulichkeit makes scarcely any sense. In other words, I think it is crap. Okay, so all right. So and here's some further some further details about it. We believe we understand the physical theory when we can think through qualitatively its experimental consequences in all simple cases, and when we have checked that the application of the theory never contains inner contradiction. Okay, so this idea of working through experimental consequences, that will be quite important for Derecht and Dieks. As you can think through qualitatively the experimental consequences of the theory in all simple cases, we will no longer have to regard quantum mechanics as an intelligible and rational. Okay, because the philosophical question here is, if you don't need visualization for understanding, then what is understanding? What does it mean to understand? if we say that, if we claim that understanding is different from explanation, but we also claim that understanding is different from visualization, then what are we left with? So that's the basic question. Now Heisenberg here gives us a hint of what could be an answer. So it's this idea of thinking through qualitatively the experimental consequences. And especially Pauli worked out this idea even more when he said that, well, eventually when we have gotten used to work with this now abstract theory, what now looks like a very abstract theory, we are used to these tools. When the tools are no longer novel for us, then the theory itself will become unchallenged. Okay, so of course you know this very well in the Oppenheim's model and explanations of deductive argument, in which the phenomenon can be explained, can be deduced from the premises containing generals and specific conditions. And like I said, only towards the turn. So this is of course a well-trodden field, but only towards the turn of this century we're interested in scientific understanding, in particular because of Heisenberg's notion here. So there's this notion of skills that understanding has. This requires has to do with having appropriate skills or appropriate abilities, and the Recht needs to give an analysis of what types of skills and what types of context. So here's what the Recht, and he published a book about it recently, 4 years ago. Understanding scientific understanding, where he gives what he calls the criterion for understanding phenomena. So a phenomenon P is understood scientifically by a scientist F, if only if she possesses an explanation P that is based on an intelligible theory T and conforms to basic epistemic value great accuracy and consistency. So here, so there's this notion of the key notion here. I mean, there's a lot, quite a bit to unpack here, but the key notion here is that understanding, scientific understanding, is defined in terms of the related notion, the related but distinct notion of intelligibility of a theory. So what does it mean? Does he have a separate definition for intelligibility? Because intelligibility seems to be a prerequisite for scientific understanding. Okay, so now we need to, now the Recht needs to give us an independent definition of what is intelligibility of a theory. Now he says, intelligibility is the value that scientists in a context C attribute to the cluster of qualities of a theory that facilitate the use of a theory, especially for building models. So it is not an intrinsic property of theory, but it's a context-dependent value that is related to the skills of scientists. So here, well, in their paper, they also distinguish between microscopic, macroscopic aims of science and also the mesoscopic. So the relevant scientific community is defined at the mesoscopic level. So this notion is pragmatic and contextual, because scientific theory is intelligible to scientists if their skills are attuned to its qualities. And so that means that judgments whether a theory is intelligible may change with historical, social, or disciplinary context. And yet that doesn't mean it's subjective. It still can be objective relative to a given context. So like the Recht puts it like this, it is compatible with objective testing of intelligibility for specific scientists in specific contexts. So he gives what he calls the criterion for intelligibility of theories. A scientific theory T is intelligible for a scientist S in a context C if they can recognize qualitatively characteristic consequence of t without performing exact calculations or without going through details. So that this is basically the old Heisenberg notion, but now in a slightly more philosophical language, more philosophical detail. Okay, since we have this notion of recognizing qualitatively characteristics that goes into the test, he also emphasizes that this criterion is not the only test. There could be other tests. And since the notion of intelligibility is related to skills, we need to say something about the skills. So he emphasized the notion of tools for understanding. Visualizability of a theory, so certain properties of theories can be tools for understanding. For example, visualizability is one such tool, as I'm now going to discuss. So how does visualizability become a tool for understanding? So visualization is a tool that allows scientists to recognize these qualitative properties of a theory, precisely as in Direct's criterion for the intelligibility of theory. So visualization facilitates understanding for that reason, because it makes the theory intelligible. It makes it more attuned to the skills of the scientific community. So a well-known example is Feynman diagrams, which summarize calculations and allow scientists to make qualitative predictions without doing calculations. So it's a visual tool to kind of summarize a very lengthy calculation, and it gives you immediate insight into the calculation without the need to do it in your head. And the prime example of that is Stephen Hawking, who was able to kind of do calculations in his head just by using visual methods in GR. Okay, so this is quantum field theory. How does this? What kinds of tools do we have in quantum gravity, especially given that in quantum gravity visualization might not be straightforward, because in quantum gravity it is often claimed that we don't have space-time, so we may not have a direct visualization of what is going on. So the question becomes, can we still have understanding? So that's actually precisely the old Schrödinger question, but now once again in the context of quantum gravity. And I think it's a good question, it's an important question. Of course, we already know that the answer will be yes, we can still have understanding, but of course the interest is in the details. What if we don't have? First of all, do we have visualization? If so, what type of visualization? And secondly, what other tools for understanding do we have? For example, for cases in which visualization might be absent. So we did a little literature search and analysis, kind of cataloging. Kind of desolating the different tools that we have in quantum gravity to do this, to gain understanding according to this notion of direct and Dietz. This is even more pressing because we don't have direct observations of quantum gravity phenomena, and we might not have them in the next few years. We do have theoretical constraints, models, and indirect testing, but so visualization models stand out as a particularly important tool, but we might not always have visualization. So one often used strategy then to derive a space-time is through a suitable approximation. Of course, the notion of visualization here also connects to notions of emergence, although I won't go into that today, but it is tied to that. So any theory of quantum gravity must reproduce the space-time of general relativity in an appropriate approximation or limit, of course, because we know that GR is a good description up to a certain accuracy of the world we see around us. So that's a prerequisite. But sometimes we may have other effective spacetimes that are derived, and those effective spacetimes can be used to gain understanding, just like also the spacetime, the 3 n-dimensional spacetime might also be a different tool to gain understanding about certain properties. And so if we can do that, then we might be able to still fulfill the criterion for the intelligibility of theories of De Recht and Diels. So how does such visualization lead to understanding of quantum gravity? And there are 2 main strategies. One is this circle of approximation interpretation. So we begin here at the well, there's no beginning and end. We could jump into the circle at any point, but let me, for sake of the argument, say that we begin here at the bottom. So we have our preferred theory of quantum gravity, where there's no space-time, there's merely some theory of quantum gravity. Now we do some suitable approximation, and we succeed in rederiving GR with a space-time. Now this we know how to interpret. And so that interpretation that we have of GR, we can use it to go back and try to set up some, at least initial interpretation of quantum gravity, right? So that maybe we might say that with a bit of analysis of this in papers on loop quantum gravity, where, well, the starting point is often a very abstract one, some SU2 algebra, quantizing the gravitational field. But using GR, okay, you know that you are somehow discretizing some space-time configurations that might be some type of knots in space-time or some type of discretization of a triangulation. And so you can use the intuitions from GR to give this initial interpretation of quantum gravity. And you know that that interpretation might not be good enough. And so what you need to do then is this extra step here in red to kind of strip from the interpretation the space-time connotations that are not appropriate, that should not be there in the quantum gravity theory. So for example, you might, yeah, I mean, you could do that in the case of loop quantum gravity that I mentioned. So you are left with the notion of SU2 algebra, the discretization of space-time, but you wouldn't necessarily have to talk about a space-time. And so you could do this several times until you are left with a reasonably good interpretation of the quantum gravity theory. And so that visualization step will certainly help in interpreting these theories, in constructing appropriate interpretation.
The stripping is to avoid being misled by those space-time connotations.
Yeah, exactly. Yeah.
Sounds like Hilbert, his Grundlagen der Geometrie. That's exactly what he says about sort of the logic of geometry has to be stripped of its.
Yeah. You should always be able to say things like beer marks or chairs. Yeah. Well, yeah, maybe. Yeah, it's interesting. Yeah. Okay, so the second way in which visualization can enter is when the space-time is not the space-time of not the usual space-time theory we look at, but some other effective space-time. And to give some flesh and bones to that, I will discuss the Duoptix expansion and show how this actually helped the heuristically. So what he did is he developed the large N limit of quantum field theories. So he began with Yang-Mills theory and with the Feynman diagram expansion, and he realized that we have these Feynman lines that tell you how color charge moves in space, basically. But then he realized that a very useful way to keep track of the color charges is by writing, by having this thick diagram here on the right. where basically you draw it not as a point particle, but as a string. And so you see that the arrows now go in different directions, thereby carrying basically the two indices of the gauge group. And then further he realized that this looked like a string diagram, and that if he took the limit where so rather than taking SU2 as the gauge group, he took SUN and taking n to be very large, that then he could get an approximation. He could reorganize his Feynman diagrams into this very nice topological expansion, where the leading term was simply a sphere and went with n squared. The second term was of order 1, was the torus. The second term goes down with 1 over n squared, and so on and so forth. So there was this terms of this rewriting or redrawing in terms of a string gives you this idea of a topological shape that you can then use to reorganize. And in fact, at each order here in the Taylor expansion, we get an infinite number of diagrams. So this is a very efficient way to calculate what otherwise you would need an infinite number of diagrams to calculate. So his kind of clever trick was to figure out, well, I have a visual method, and that visual method simply summarizes all my calculations. So this is what we call an effective space-time, because this is not the space-time of Yang-Mills theory. I mean, not just space-time, but the topological shapes that we see in space here, they are not the shapes of any particle in any sense. It's some other auxiliary thing that we find. Okay, so then we can summarize the classification of various examples that we looked at from the literature into 3 tools. So one is approximations, where and I should say now 3 tools apart from visualization. So here I have emphasized the role, the 2 different roles of visualization, but now we might move into examples where we don't want visualization, or at least we don't want to use it up front. So what other tools do we have then? We have approximations, where we use approximative relations between theories, for example, using a classical limit to understand a quantum theory. And that's often combined with visualization. So approximations often allow for visualization, like in the Heuristic case. That was an example of an approximation, of a visualization that we can make in a case of approximation. Other tools are similarities between concepts, in the use of concepts between theories, and those could be either formal similarities or interpretive similarities. As an example is the formal similarity of charge conservation between Maxwell's theory and other theories in physics, for example, in the probability conservation in quantum mechanics and the development also of the de Broglie-Bohm theory. There is that analogy between probability conservation and charge conservation. So those are formal similarities that also help you in developing new theories. So comparing, I call them similar because it's really a very broad form of comparison between 2 theories. And you could also have internal criteria that can be used to interpret the concepts or terms within a given theory. And again, those internal criteria can be formal or similar. So where does duality fall here in the spectrum of approximation, similar, or internal? So dualities contribute, I would argue, to all 3 tools. Contributes to approximations in the sense that a duality can, of course, be used to visualize quantum gravity using an effective space-time. For example, in T-duality, and especially in gauge gravity duality, we use the ADS spacetime is a very useful tool to visualize what otherwise is a very intractable, strongly coupled problem in field theory. So that would be a case of approximation of an effective spacetime. Nice recent example is the effective duality between a 4-dimensional black hole in ADS and the 3-dimensional strange metal. So it turns out that condensed matter, experimental condensed matter physicists, including some of my colleagues in Amsterdam, they measure so-called strange metals, which are metals like copper superconducting materials, so layers of copper oxides alternating with other oxides, where they do basically a photoelectric effect, and then they measure the photons that come out, the angle of the photons, and they try to therefore measure the correlation functions. And solid state physics, the usual theory of solid state physics, could in no way explain the experiment that they did. So none of the current theories, but they could explain it using this ADS duality, a specific case, a quasi-duality. So using a black hole in 4 dimensions and using the linearized Einstein differential equation. So this is a case of not some theoretical science, but actually some experimental science where you get your hands dirty in the lab, where you can make scientific discoveries by using this kind of tool. Well, and this where these people made this advancement using those approximations. So those are the case of approximations. Those are, of course, very well-known tools. Then similarities and dualities also contribute to similarity. So besides the formal similarities, we have interpretative similarities. For example, the Mandelstam realization that monopoles could give a magnetic analog of condensation of Cooper pairs. We already discussed this case for confinement. Holographic dualities are also an example of this, because once you realize that there is this formal similarity, then you can use topological expansion to do actual calculations in Yang-Mills theory using string theory. And likewise for cases like particle versus soliton dualities. So this is a case where dualities contribute to similarity. All right, so I'm going to end here, and also today I will be earlier have some discussion. So summary is that the theoretical function, we're interested in a theory T that satisfies the schema, while in the heuristic function we always go beyond the schema. That is actually the definition of the heuristic function. And so the distinction between duality and effective duality is relevant. So we saw 3 ways in which emergence can take place when we have duality. It can take place through an effective duality, or through emergence alongside duality, or through epistemic emergence. And maybe there are other cases, but in any case, these are 3 cases that appear in the literature. 2 ways in which space-time can be derived using visualization. So where visualization can be used for understanding, even in theories where you don't have a fundamental space-time. One is to get the space-time of general relativity, and we saw how it must always reappear, and so we can always use that in this Hilbertian way to kind of reinterpret the fundamental theory. And the second one is the more adventurous one, where you don't even take recourse to general relativity, but you develop some other kind of space-time, for example, an effective space-time, like the one we saw for the topological expansion of Yang-Mills, where it's not supposed to be a realistic space-time in any sense, but just a useful tool, that can nevertheless help you visualize things and make progress. But of course, we saw that visualization, since it is not an indispensable tool, there must be other ways to gain understanding in quantum gravity. And we saw some of those. We saw 3 of those tools. So approximation, similarity, and internal criteria. Okay, so here's a list of the papers on which this is based. And I would like to thank you for listening, also for the other.
But on the last part, on space-time, so I was wondering why you were tying this idea of visualization to space-time, but then I thought where you were doing the dualities, it's very interesting. But still, maybe we should not restrict visualization to space-time. Because you say it's not physical space, visualization space, but even how would you think of a causal network or a directed graph?
Yeah.
In your classification, would those count as a kind of non-spatial temporal visualization or quasi-spatial temporal visualization, sorry? Or is your notion of effective space-time super-liberal in a way, so that would also count kind of space-time or just as other sorts of spatial visualization? Because in a way, I think the way of thinking of it would be more like in order to visualize something with enough structure, to have a mental representation that seems to be embedded in three-dimensional space, something like that. But of course, just like we can think of a surface, we don't need to. I know this is what I mean.
Thanks for making that distinction. That's an important distinction. For the purpose of the talk, I didn't make that, but in the paper we do make that distinction between the visualization. So you could have, of course, many kinds of visualizations that are not in space-time, like also sometimes, drawing a graph to quantities that vary with respect to each other. That's also kind of visualization that is not space-time visualization. So I agree that we should make that distinction. And indeed, even and in our paper, one of the papers we did go a little bit into that and what do we mean by space-time visualization. So there is a question of what do you regard as space-time visualization? What kind of structure do you need for that? Do you need continuous structure? Do you need topological structure, differentiable structure, and so on? So in our paper, we considered things like Hesse diagrams and causal set theory, and we kind of made a distinction between the case where we simply have the causal, a kind of causal structure, but without calling it necessarily causal in time, so kind of separate from time. So conceptually, at least, you can read those papers on causal set theory without reading time into it. So you can think of it in terms of just a positive structure. There are some papers even that go to the logic of that. So you could give more of a logic type interpretation without necessarily giving it a space-time interpretation. So I think you can strip that off completely from that, and that we don't. That is not that we don't call a space-time visualization. But of course, you can make this step of giving it an explicitly time interpretation or even an explicitly space-time interpretation. And again, within that, you can debate what are the technical conditions that you need for that. To be honest, I don't quite remember exactly what was our definition in the paper for what we regarded as space-time. I think we did I think we did say that space-time required a topological structure. Yeah, that's for sure. But maybe not continuous structure. I should check that. Maybe not the differential structure. I should actually check those details. But yeah, that becomes more of a technical discussion. What do you regard as, what do you count as spatiotemporal structure? But yeah, thanks for making that distinction.
So, Sebastian. And so
I cannot hear very well. From here, you must speak a bit more nearer to the microphone. Okay, thank you very much, Sebastian. Can you hear me? Yes?
Yeah, I can hear you.
Okay, thank you very much for the whole course that you gave during the school and for being there in actuality. And this last lecture was especially wonderful. I appreciate very much. I have a comment about the final part on understanding. Seems to me that the notion of explanation introduced in philosophy of science at the beginning was above all a logical epistemological notion without psychological and pragmatic aspects, but at the end of the story, of the long story, with interpretation by Van Frasse and many others, became something completely pragmatic without with no longer epistemological and logical aspects. It seems also that the notion of direct that you presented is strongly pragmatic. Logical epistemological aspects are almost completely eliminated. And indeed, understanding, comprehension is clearly something human. So probably it is unavoidable that part of the notion is psychological, not completely a logical or epistemological notion. So clearly it is a part, but the notion of intelligibility as presented before seems almost completely devoid of epistemological and logical value. Probably it is possible to say something more. Also, the criteria that you propose concerning duality are a bit more logical and epistemological, not completely, because clearly there are persons that must understand physics, and so persons are constituted in a certain way. It is unavoidably human, something human. Another small point is that probably it's not all important what is comprehensible for physicists, but in general there is a problem of comprehension for everyone, and so there is a problem of understanding that is bigger than what physicists are persons with a long training, a special training, and it is clear that what is understandable for them is not in general understandable. Perhaps it is interesting also to speak about what is understandable for human persons in general with a more generic formation. This seems also a point. Another point that I find important about understanding is the fact that there is also a logical understanding, probably explained quite well through the notion of Turing machine, that is the notion of calculability, and this is a notion complementary to the notion of geometrical or visual representation. Visual representation is something continuous. On the contrary, understanding in the logical sense is something connected with the notion of calculation, and clearly we have limit of length of a chain of the computation, but the single step of a computation is something comprehensible for us, and I think we must not neglect this aspect of comprehension. There is a gap between the comprehension in the sense of calculability and the sense of visualization, indeed, because when we attempt to build the notion of continuum through calculability, we arrive at a very strange notion of continuity, a mathematical notion of continuity that is strongly counterintuitive and not particularly understandable for us. Last point.
Enzo, can you hear me?
Yes.
Sorry, we have some issues with the more general audio. So wait a second.
Yes. Oh, sorry.
Sorry everyone, but like the internet connection went down. So Enzo, what were you saying?
Okay. Yeah. When you arrived, at what point of my long comment?
Well, so you were saying, I mean, you said several things. Yeah, you were saying that there is also a logical point about understanding.
Yes. One thing that I would like to emphasize is this one, that is with respect to direct definition, seems that perhaps it is better to have a bit a partial logical epistemological aspect in the definition of intelligibility and not a completely pragmatic point of view. This is one point. The second point was about calculability. Turing, the notion of calculability through a Turing machine is comprehensible for us, and indeed between calculability in this sense and visualization there is a sort of gap. Indeed, we are not the notion of continuum that we attempt to build on the basis of natural number is strongly counterintuitive and so not completely understandable. So there is the complementarity between calculability and the visualization. This is the second point. Third point is that it is a question. Do you think that in loop quantum gravity string theory, really we have a fundamental level that is completely devoid of spatio-temporal or geometrical aspects, or either or it is that this geometrical aspect, it is representation through geometry is something strongly dependent on what happened from a physical point of view, and so in a certain sense a bit of visualization still stay with this possible speculative ontologies of loop and strings. Okay, thank you very much again for your presentation.
Okay, yeah, thank you very much for that question. So yeah, it's a very interesting question. So your 3 points, so maybe to begin with the third one, so about the question about string theory, quantum gravity. I would say that is more, that is, at least as I understand the question, that is a speculative question about whether whatever final theory there is, if there is a final theory, whether that will be a spatial temporal theory or not. To be honest, I would leave that as a question for the physicists to answer, because in the sense that, you know, it depends on what that final theory turns out to be. I mean, I could try to make guesses or conjectures based on what we know now, but yeah, I would say that that is, to my mind at least, that's more of a physics question rather than a philosophical question, if I understood it correctly. In string theory, it does seem like we interchange spatio-temporal structures with things that are not spatio-temporal in the same way. But whether that goes into in theory, we don't know. I mean, there are people who say that, yeah, in theory will not be spatio-temporal in that sense because these matrices are not in space-time, and so on. Space-time is only derived as the corpse graining over these matrices. But again, that really requires looking into speculative physics that we don't have right now. The second point is let me see. Yeah, about the calculation.
Calculation through the notion of Turing machine is quite comprehensible Turing machine. Yes.
So let me clarify that the role of visualization for the Recht, the role of visualization is that it helps us do those calculations without actually doing them. So he says, and that ties in with his criterion of intelligibility, that we have methods for, not for doing calculations, but for knowing what is the outcome, for guessing the outcome of the calculation without actually doing the calculation. So we have other forms of reasoning according to the Recht that are non-calculational, but that still give us the right answer. So that's the role of those tools. Now, people have criticized him because they say, well, and I think that there is a fair criticism there that this seems very much, the notion of calculation seems very much tied to physics. I mean, there are other, in biology, maybe the thing that one does is not a calculation, but something else. And likewise in other sciences. So there is a question of how do you generalize this to not the non-physical sciences. And then the first point that you made, yeah, people, again, well, when I gave this talk elsewhere, somebody asked about, well, how does this relate to Van Fraassen, and is the Recht assuming a realist position? Is this incompatible with realism? So I would say in this, the Recht is neither realist nor anti-realist, in the sense that he doesn't. So, for example, when Carnap discusses understanding, Carnap says understanding a physical theory is knowing the truth conditions for the sentences of the theory. So, for Carnap, understanding a theory is tied to the notion of truth. So that would be, nowadays we would view that as a realist notion of understanding. So you could say, okay, I'm going to strengthen the Recht's notion by adding this notion of truth. If one is a realist, that's something one could do. The Recht argues against this, and I think he has a point, because he says, well, you know, when we understand theories, the understanding is not given by the truth, or at least not always. So we can even gain understanding using the phlogiston theory. So the phlogiston theory, we know it's false, but it still could give us understanding of something. So there is, anyway, there is some debate to be had there about what is the notion of false theory. Could false theories lead to understanding? The Recht claims that they do, and other people like also Hasso Cheng, they make similar arguments along those lines. So that's a debate that you could have. And then against Van Fraassen, because the Recht is also does not commit to anti-realist in that sense that he's, I mean, so even though it's pragmatic, it is not pragmatic in the sense that it's irrelevant for, it's not epistemic. So the Recht very clearly says that even though I am pragmatic in the sense that I bring in the societal context, all of that is very important, but precisely that is also relevant to epistemology. So in that sense, I think we should distinguish logic, metaphysics, semantics from the epistemic project that the Recht is engaged in. So he would claim that what he's doing is epistemic, even though he's bringing in this kind of wider aspect. And I think that connects with what you were saying earlier. So this pragmatic aspect comes in through the context.
Thank you very much.
Okay, so we're almost at the end of our time, so we have time for one last question, and I saw that Anastasia.
Yeah, I just have a very small follow-up to this idea of understanding, if I may. I was just wondering, because your criteria that you talked about, they have this kind of a way to have infinite amount of ad hoc hypothesis due to, empirical adequacy and consistency, like, does not protect us from those ad hoc hypotheses. But since you said that something like this is not the problem for you, right? So if like something like phlogiston can be still giving us some kind of understanding, then I guess we shouldn't even care then in this sense about the ad hoc stuff that we can add up to our theories and still call it understanding.
Sorry, the sound is sometimes a bit bad. I didn't catch the last part of the sentence. We shouldn't care.
So it doesn't matter if we have a lot of ad hoc stuff in our theory, it can still be understanding, because of what your previous reply is like, it doesn't matter. Like for phlogiston can still give us some understanding. So this is not the problem for you.
This is within the Recht theory, which here I have, for the sake of this argument, I have endorsed. Yes, that is the case. The truth. I mean, he still does have, as you remarked, the empirical adequacy. So you could argue whether whether phlogiston is empirically adequate. Maybe it was within a given regime. So probably there is a regime of phenomena where the phlogiston theory was empirically adequate. That's at least what Hasso Cheng, I believe, argues. So if you buy the argument, then even though the theory is not true, it is still empirically adequate, and so it still satisfies the Recht's argument, and so it can still give you understanding. And I think, I mean, in that sense, I think de Recht seems to have a point that the notion of understanding, unlike other notions that we have in philosophy, seems to be more liberal in that sense that it allows this kind of theory, because it captures something that we wouldn't be able to capture if we really limit ourselves to theories that are true.
Yeah, but then we can also have basically a metaphysical theory, like here, like satisfying those criteria of being empirically adequate and, you know, consistent. So,
Sorry, again?
like we can also have a metaphysical theory, and it's not just this criteria for understanding can also apply for a metaphysical theory. That's what I'm saying. Like it can be empirically adequate and consistent also. So there is no strict border that I see here.
You mean like adding additional metaphysical stuff that doesn't change anything to the theory?
Yeah.
Yeah, I guess the question would be whether it gives you more understanding than when that metaphysical stuff is not there, when you don't have the metaphysical stuff. So I mean, so I guess what you are saying, maybe a different way to put what you are saying could be two things. I mean, I do see the point actually. So one question could be for the Recht is, how does empirical adequacy seems to be put in maybe a little bit by hand. So how does empirical adequacy connect to the intelligibility of the theory? So is there some sort of coherence between the two things? So does it put in this metaphysical stuff, does it add not only to the understanding but also to the empirical adequacy or not? So it seems to be that to avoid those kinds of cases, maybe one would need to say more about how empirical adequacy connects to the rest of it.
Yeah.
Yeah, I think that's a question for the Recht. Yes.
Thank you so much. It was very interesting. Thank you.